Okay, so this begins kind of the last chunk of material, so I won't finish all of the last remaining bit. Today I'll have to post a supplemental lecture um, to make up the rest, but um, the last, so like half of problem set B and all of problem set C contain material. So problem set C contains material from chapter 13 and 14. Problem set B just has a few problems from chapter 13. But by the end of today's lecture, I believe you should be able to do most of the chapter 13 problems. So as I put in chat, it's a lot easier if you read along in the notes because like the previous couple of chapters, it's a lot of visual stuff. It just makes it a lot easier. The graphs themselves, at least the smaller graphs, are pretty easy um, to jot down. That's not the problem. The problem is writing down the matrices for the most part. So anyway, I'd gotten a couple of emails or Elms messages from people saying that they had tried to read ahead through the graph theory bit, and they're a little bit confused. So that's why I decided to do today as a graph theory lecture instead of the problem section or problem session. So I'm still going to do a problem session sometime either Friday afternoon or sometime over the weekend, and I'll let you all know when that's going to be. But anyway, so graph theory. I know that a lot of you probably have some experience with graph theory stuff, but I'm going to assume that you've never seen a graph before in your life. So what is a graph? A graph is just a collection of vertices and edges. So the vertices or nodes might be, I'm going to number them just to keep track of them. They don't have to be represented this way. They could be represented literally as dots, but I'm going to, so keeping with how they're drawn on the first page of the notes. So this is the following graph here. So we have those circles are our vertices, and our edges are drawn in this example, we'll say like this. Okay, so a graph is some diagram, if you like, involving vertices and edges. So the way that they are labeled here, so this is the very first example. This example is going to be used a lot throughout this section. So labeling it here, this is vertex 1, this is vertex 3, this is vertex 6, this is vertex 2, this is vertex 4, this is 5, and this is 7. So 7 total vertices. Maybe I'll put my 3 here, 1 here, there we go. Okay, so a vertex is a point and an edge is a one-dimensional connector here. And so so this is an example of a graph. Graph theory is the study of things like this. Now, there's a lot of forms that a graph can come in. This is a particularly nice example called a simple connected graph. So quick definition, so a graph is simple. So a graph is simple if it has no multiple edges and no loops. So an example of multiple edges would be, say, a 3-vertex graph where maybe I have 3 edges connected between those 2 vertices and then just 1 here. Okay, oh, I'm off camera. Here we go. So yeah, so notice here between these 2 vertices I have 3 edges. That's an example of a multiple edge. A loop would be I have maybe 2 vertices, but one of them has an edge connected to itself. Okay, this would be a loop. Okay, so no multiple edges, so nothing like this, and no loops, so nothing like that. Okay, another definition, a graph is connected. So a graph is connected if it's a single connected piece. So you can think about this as being path connected, in the sense that there's a continuous path between any two vertices. So, for instance, an example of a graph that is not connected would be, take this graph I have here, except instead of there being this 2-3 edge, they're just disconnected. So you might say, wait, isn't that two graphs? Well, I could call it two graphs, but because it's appearing here in the same place, I can think of this as being a single graph, but it's disconnected, meaning vertices over here and vertices over here, there's no path between them, right? There's no way that I can reach one from the other side. So this would be an example of a disconnected graph. And so a simple connected graph is one that satisfies both of these things. So no multiple edges, no loops, and it's one single connected piece. So this is an example of a simple connected graph. And remember, a graph itself is just a collection of vertices and edges, so nothing else is needed there. No other assumptions. Okay, so a couple of quantities that are going to be very important. So a few more definitions that are central to studying graphs. So a few more definitions. One, the degree of a vertex is the number of edges connected to the vertex. Okay, so that's the degree of a vertex. Let's go back to our example for a second. So now we can just go piece by piece here. So start here with the leftmost. What's the degree of this vertex? 2, because there are two edges connected to it. So here degree is 2. I'm gonna write it as little d here. So this is 2. What's the degree of this vertex? It's also 2. What's the degree of vertex 3? It is 3. There's 3 edges here. What's the degree of vertex 2? It's also 3. All right, there are 3 edges connected to it. And all of my other vertices have degree 2. Okay, so that's what degree of a vertex means. Okay. So, more definitions for a simple graph G within vertices. The degree matrix D is the n by n diagonal matrix that looks like this. So this is D sub 1, 1, D sub 2, 2, D sub 3, 3, all the way to D sub n, n. And all these are 0. All the off-diagonal entries are 0. Okay, such that D sub I equals the degree of vertex I. So it's just a diagonal matrix you get where you've put the degrees of each of the vertices arranged in this way on the diagonal of this matrix. Okay. So then coming back to our example really quickly. So this matrix has 7 vertices, so this would be a 7 by 7 matrix that had 0 entries everywhere except on the diagonal. And what would its entries down the diagonal be? Let's just read off. It would be 2, 3, 3, and the rest of them 2s. Right? So in this, so in our example, D would be 2, 3, 3, 2, 2, 2, 2, and 0 everywhere else. Okay. Okay, so we're almost getting to the actual quantities that we're going to be referring to throughout the rest of this section. So that's the degree matrix. Another definition for a simple graph G. The adjacency matrix A is the symmetric matrix such that A sub ij, that is little a sub ij, is equal to 1 if vertices I and j are connected by an edge and a sub ij is equal to 0 otherwise. Okay, so why is it symmetric? Because if vertices I and j are connected by an edge, then vertices j and I are connected by an edge. The notion of being connected imparts no idea of orientation. We don't care. We're not going to differentiate between I being connected to j and j being connected to I. As long as they're connected by an edge, we don't care. And so it's necessarily, by definition, it's symmetric. Okay, so that's where the symmetry comes from. One more definition, and then we're able to actually start talking about stuff. So for a simple graph G, the Laplacian matrix L is defined by L is equal to D, the degree matrix, minus A, the adjacency matrix. Okay. Now, if you know anything about graph theory, you might recognize that this is one example of what's called a Laplacian matrix, but there are different Laplacian matrices. This isn't the only thing, but for us, this is the only thing we're going to refer to as Laplacian matrix, and we're just going to call it the Laplacian matrix. Technically, it has a more specific name, but for us, this is just going to be called the Laplacian matrix. So in your exercises, whenever Laplacian matrix is referred to, this is what's meant. Okay. All right. So going back then, this is where having the notes handy is good, because I'm not going to have to read these things. Or I'm not going to have to actually write out these things. So in this example that we did on the next page of the notes, which is page 5 in chapter 13, has all these quantities listed. So page 5 in chapter 13 has all these quantities listed for our example. Okay. So you can see D, I already had written that down the page. So the degree matrix, all the degrees of every single vertex was 2, except for vertices 2 and 3 had degree 3. Those are the only vertices that were connected to more than 2 edges. The adjacency matrix, you can see looking next, you can see the adjacency matrix. You might actually notice something automatically about where those entries are and how those entries relate to the degree matrix. But the adjacency matrix is listed next. So remember, the adjacency matrix is the matrix. It's necessarily symmetric, and you can figure out a little a sub ij entry. It's either 1 or 0. It's 1 if vertices I and j are connected directly by an edge, not like a sequence of edges or anything, and 0 otherwise. Okay, so if vertices I and j are directly connected by an edge, the entry a sub ij is 1. If not, then a sub ij is 0. Okay, and then the Laplacian matrix is just the difference. It's just D minus A. It's just the degree matrix minus the adjacency matrix. And so it turns out that both the adjacency matrix and the Laplacian matrix itself contain all the info about the graph. So you can reconstruct the graph entirely from either L or A. Okay, but L is what we're going to refer to a lot because the main thing that we're going to want to do to analyze graphs is what's called partitioning graphs, and we're going to do that through analyzing L, the Laplacian matrix. Okay, so a couple more definitions because this is going to nicely tie in some of the graph analysis that we're going to do. So first definition is the definition of a walk. So a walk from vertex I to vertex j is an alternating series of connected vertices and edges that starts with vertex I and ends with vertex j. So I didn't say anything else other than that. Okay, so there's no restrictions on repeating edges or vertices, so no restrictions on repetition. So going back to our example, so here's my graph. A walk from 1 to 2. Here's one. I go from 1 to 3 and 3 to 2. That's one walk. Another is I go from 1 to 6, from 6 to 3, and from 3 to 2. Another is I go from 1 to 6, 6 to 3, 3 to 1, 1 to 6, 6 to 3, and 3 to 2. That's one. Or I could have taffed around over here as well. So the point is that there's absolutely no restriction on repeating edges. It's just that I start at, so for a walk from vertex 1 to vertex 2, I start at 1 and I end at 2. Other than that, I don't. I'm not making any claims. So no restrictions on repetition at all. Okay, so here is a very nice theorem that tells you something about what the adjacency matrix is saying. I'm not going to prove this, although you can actually, I believe he proves it in the notes. Yeah, he proves it in the notes. It's pretty quick, but I'm not gonna write that down. So theorem: if A is the n by n adjacency matrix of a graph with n vertices, then for every integer k bigger than or equal to 1, the ijth entry of a to the k is equal to the number of walks of length k from vertex I to vertex j. So this is me counting the total number of walks of a specified length and saying that that's equal to the ijth entry of this a to the k. And this is kind of what the adjacency matrix is telling you. So for those of you that have already seen some graph theory, you might already know this fact, or if you don't, but you're only vaguely familiar with graph theory, it shouldn't surprise you too much because you probably already know that graph theory is, like intimately connected with questions of counting and combinatorics and these things, especially combinatorics. Graphs are essentially combinatorial objects entirely, and so they're very like fundamentally connected in this way to questions of counting. So another quick definition, although all of you already know this. In fact, I think I did this during the review at the very beginning of the semester. So the trace of an n by n matrix is the sum of its diagonal entries. Okay. So you've probably seen that before. And the reason for defining that here is I have one more nice thing about basic graph analysis, which is the number of triangles in a graph is equal to 1/6 times the trace of the adjacency matrix cubed. This might seem like a really weird fact. So where does this come from? The proof of this fact actually relies on this previous theorem, and this is also done in the notes on page 6, but just quickly going through the reasoning behind the proof. So we've already seen that a walk of length 3 from a vertex to itself is a triangle. That's one way of defining a triangle as part of a graph. And that triangle yields 2 walks. One where you go around in one direction and the other where you go around in the opposite direction. So a triangle determines 2 different walks around that triangle. And those are defined by the direction you go around the triangle. Okay. So then if a vertex is contained in a triangle, then that corresponding entry in the adjacency matrix cubed, right, walk of length 3, the entry corresponding to that is 2 because of this previous fact I just said. And so from that, if you look at the trace, that is the sum of those diagonal entries, this is going to be twice the number of vertices contained in triangles. Okay, so you're just summing A cubed, the adjacency matrix cubed. And so since the ith entries, right, since every diagonal entry of A cubed is 2 on account of that, that trace is going to be equal to 2 times the number of vertices contained in triangles. But since a triangle contains 3 vertices, then the trace of A cubed is 6 times, right? 3 times 2 times the number of triangles. So 6 times the number of triangles, so then the number of triangles is 1/6 times the trace of A cubed. If you couldn't follow that because I was saying it in words and not writing it down, you should have a look page 6 in the notes, and it explains why. So it also mentions that the same approach doesn't actually work for squares, pentagons, hexagons, and so on, and it questions why that is. So if you think about those configurations, you'll quickly realize why it doesn't work for squares and higher, and why that reasoning only works for triangles. The hint is that, well, triangles only have 3 edges, right? There's not a whole lot of freedom there. Okay, so now we're getting to kind of the meat of this chapter, which is graph partitioning. So this is kind of the big tool that we're going to talk about when it comes to analyzing graphs. So what we just mentioned was some really cool stuff about graphs and the relationship between a couple of those quantities and actually counting things related to graphs. But graph partitioning is going to be the like bread and butter of this section. Graph partitioning is exactly what it sounds like. It is taking a graph and splitting it in some reasonable way. Okay, we are going to have a particular method that we're going to apply. In general, it's not the only method, and we're going to see limitations of the method that we're going to do. But for us, it is going to be essentially the method we're going to use. So the idea is splitting a graph in a reasonable way, with both splitting and reasonable in quotation marks. The splitting should barely be in quotations because we are essentially going to be splitting the graph. That's not really in dispute. The reasonable, though, should definitely be in quotation marks because that has a lot of explanation that has to come with it. Okay, so going back to our original example, so in this graph, you could think about this as properly described as a triangle connected to a square. And so looking at it like that, maybe in your mind, when you automatically see this and say, yeah, it's like this graph has 2 main pieces. Like it's got the triangle piece and it's got the square piece. And yeah, they're connected by this edge, but in your mind, maybe already you're kind of like ignoring this edge. So in your mind, what you're already doing is splitting this graph in some way. Okay, so we want to think about doing that, except not just for graphs like this, for more complicated graphs, and we want to come up with like a rigorous explanation for why this splitting makes sense or why it's even nice or something we'd want to do in the first place. Okay, so quick definition. So given a graph G with n vertices, we'll call the vertices set the set containing the numbers 1 through n. Okay, for an integer k that's bigger than or equal to 2. For our purposes, a 1 partition is not a partition at all. It's just the graph itself. So a k partition of G is a partition of the vertices into k subsets v sub 1 through v sub k, such that the subsets are disjoint, so they don't overlap. They've got empty intersection. Many ways you could characterize that. So such that the subsets do not overlap and their union is all of V. So they are disjoint and they're exhaustive in the sense that they fill out the set of all vertices. Okay. So in that case, we will write that a partition is P, which is V1, V2 through VK. And a two partition is just called a partition. So a partition into two pieces is just called a partition. So the partition that I mentioned earlier in our first example, just splitting that triangle and that square apart, that would be an example of a two partition because it breaks it into two pieces. Okay, so with our example brought back, if I was going to split this graph in exactly the way that I specified by considering this triangle and this square as two separate pieces, it would be vertices 1, 3, and 6 taken in one piece and 2, 4, 5, and 7 taken in the other. So, example, splitting our previous example in the obvious way. We get the partition or two partition, which is following this notation. This is P, where V sub 1 is going to be that first triangle. Let me bring it back. It's going to be that first triangle, which includes vertices 1, 3, and 6. And then in the second vertex set, it's everything else. So I could actually read it, knowing I have 7 vertices, I could just read it off. But looking at the picture, it's vertices 2, 4, 5, and 7. So this is 2, 4, 5, and 7. Okay. Oh, so I see a question. Can you go past 2 and then come back in the walk? Yes. So for the walk, you can just because you reach 2 doesn't mean you have to stop immediately. So you can keep going for as many times as you want to. So then the main thing, of course, that was important when we were talking about the adjacency matrix was that was walks of a specified length. Right, so the second that you make an imposition, right, you impose that your walk is going to be k length, then there start to be restrictions. But if I just talk about a completely unrestricted walk, if I just say a walk from vertex I to vertex j, I'm allowed to taff around all I want to, going around in circles for as long as I can tolerate. So yeah, I can definitely hit 2 and keep going. Okay, so another way of looking at this, going back here, another way of viewing this partition is that we have taken this graph and just removed the 2, 3 edge, right? So we've removed the 2, 3 edge is another way of viewing this. Okay. So, another definition, a lot of terminology in this chapter. So another definition, this is important, this is definition of the cut of a graph. So for a partition or two partition, so for a partition P of G, where P is a two partition, so V1, V2, we define the cut of P denoted cut P as the number of edges joining a vertex in V1 with a vertex in V2. So this is the number of edges joining a vertex in V1 with a vertex in V2. Well, again, returning to this example. So thinking of the partition of this graph as 1, 3, 6 and vertices 2, 4, 5, 7, what is the cut of that partition? The cut of that partition is 1, because there is only a single edge, the 2, 3 edge, that connects a vertex in V1 with a vertex in V2. V1 is this triangle and V2 is this square. So the cut is 1. I'll state that. Oh, I need more room. So note in our example, the cut of the partition is 1. Okay. Now, another definition now that we have cut defined. So a minimum cut is a partition P of a graph. Remember, a partition is necessarily into two pieces, because we called it a two partition. So a partition means a two partition. So a minimum cut's a partition P of a graph G in a manner that minimizes cut P. Okay, so this minimizes cut P. i.e., it is the minimum number of edges we need to remove the partition, it's the minimum number of edges we need to remove to partition the graph. Okay, i.e., it is the minimum number of edges we need to remove to partition the graph. So again, recalling our previous example, we had already previously mentioned that one way of looking at the partition was that we had removed the 2, 3 edge. So in this case, the cut we mentioned before is the minimum cut. Or the partition we mentioned before is the minimum cut because the least amount of edges I need to remove is 1 here. Okay, to partition those. Okay. So finally, we have another example. I can't draw all of these because usually the graphs are too big. It would take me too long, but these are simple enough. So I have this modified bow tie. So I have so here's my graph. Let me see how they label it. So this is 1, 2, 3, 4, 5, 6. So 6 vertices labeled in this way. This is what my graph looks like. So consider this graph. So I want to partition this into 2 pieces. Well, if I have no guidance as to what my 2 pieces need to look like, right? I could always do something silly here and just remove the 5, 6 edge. All right, so note, if I remove the 5, 6 edge, I get a partition that is a minimum cut. Right. Okay. So again, just remember what minimum cut is. A minimum cut is a partition that minimizes the cut of the partition. The cut of the partition is this number of edges connecting a vertex in one piece of the partition to a vertex in the other. Okay. And so if I were to consider the partition where I have vertices 1, 2, 3, 4, 5 together and vertex 6 off on its own, right? That is a partition, and it's actually a minimum cut because I only need to remove one edge to do that. Okay. Now, why wouldn't I want to do that? Well, this is a very, as the notes say, this is a very unbalanced way of partitioning the graph. So this is a minimum cut, but this is a very unbalanced way of partitioning the graph. So the idea is that I want to study this graph, and I want to partition the graph to help me study the graph. And just using the minimum cut is not going to cut it because, well, this is really like not a great way of trying to preserve the same amount of info in each partition. So for various reasons, what we actually want to do is we want to keep the cut as small as possible while also keeping the size of the partition sets or the partition subsets roughly the same. So that's why just using the minimum cut is not good enough. Okay. So this is an unbalanced way of doing it. So what do we want? So what do we want? And the answer is we want to find a partition which minimizes the cut while also keeping the sizes of its subsets roughly the same. So we want a partition P of G. So P, since it's a partition, it splits into two vertex sets, V1 and V2, such that cut P is minimized, but also the size of V1 is approximately the size of V2. So the vertex sets are approximately the same size. Now we're not always going to be able to do that, but this is the goal. All right, this is our goal here. Okay, and so the way that we want to do this is the Fiedler method. So we're going to do this via the Fiedler method. Okay, and the Fiedler method is basically the main point of this chapter. So from this point on, from what page we're on, 6 or 7, 8. So from page 8 until you get to the MATLAB portion of this chapter, it's going to be discussing the Fiedler method. And there's going to be a ton of examples here, and that's what we're going to go over. So the Fiedler method is a way of partitioning the graph, and it's a very straightforward way of going about it, and it's completely amenable to MATLAB and computations in that way. Basically, what I'm going to do is I'm going to state like the very, very basic form of using the Fiedler method, and then go through some examples in the notes. So that's the idea. At the end of this chapter, he goes through like a full proof of why the Fiedler method gives you what you want. I'm going to skip all of that. I'm going to skip all the theoretical stuff, and you can read that if you're interested in it. But that's the deal. Okay, so question is, how or what is the Fiedler method? So the answer to that is coming up. So this is the basic Fiedler method. Okay. So there's a couple of things. So one, if G is a simple connected graph, with n vertices, and if L is its Laplacian matrix, then L has n real eigenvalues, say lambda 1 through lambda n, satisfying the following. So the first eigenvalue is 0. The second eigenvalue is positive, or strictly bigger than the first eigenvalue. The remaining eigenvalues dominate one another in this sense. And this is what I have. Okay. So the first eigenvalue for the Laplacian matrix associated to a simple connected graph is always 0. The second eigenvalue, labeled like this, right, in ascending order, is always positive. It is always guaranteed to be strictly bigger than 0. Now the remaining inequalities are inclusive. Okay, but this one is not, and that's important. Okay, because it's going to turn out that this second eigenvalue in this way has a special name. This is called the Fiedler value. Okay. So this second eigenvalue in this way is called the Fiedler value. It's the smallest positive eigenvalue that this Laplacian matrix has. And quick definition, the Fiedler vector so the Fiedler vector of a graph G is an eigenvector. I was going to say the eigenvector, but you know they're not unique. So it's an eigenvector associated to the Fiedler value of G. Okay. It mentions in the notes that in general, if you have n vertices, right, could be a really big matrix, and so the corresponding eigenspace corresponding to the Fiedler vector may be multiple, or corresponding to a Fiedler value, sorry, may be multidimensional. So we don't care too much about that right now. So I'll mention some complications that arise using this Fiedler method. So again, returning to our example, we had previously computed the Laplacian matrix, so I didn't actually write it down because it was too big, but you can see this on page 10 of the notes. So on page 10 of chapter 13, you have Laplacian written down for this example. Okay, and so once you have that Laplacian down, you can find its eigenvalues in short order. So finding the eigenvalues is no problem. So look at the list of eigenvalues there listed below it. The smallest one, of course, is 0. That's the first eigenvalue. The second eigenvalue is 0.3588. The next eigenvalue is 2, and so on, right? There's a whole list of eigenvalues there. And it says, note the Fiedler value is 0.3588. It's the smallest positive eigenvalue that it has. You can also find a Fiedler vector, so an associated eigenvector to that eigenvalue, the Fiedler value. And so what you get is the vector v. So you get a Fiedler vector v. So I have Fiedler value lambda sub 2. The Fiedler vector, you can call it v, you can call it v sub 2, whatever you call it. What is the thing that you do here? So part 2 in the Fiedler method. Use the signs of the Fiedler vector that is the signs of the entries, I should say, in the Fiedler vector. So use the signs of the entries in the Fiedler vector to come up with your desired partition. Okay, so what do I mean by that? So look at page 10 in chapter 13. So in page 10 in chapter 13, I have at the top of the page the associated Laplacian for my graph. Writing out its eigenvalues, there they are on the next line. So it has 7 eigenvalues. So 7 real eigenvalues, they're listed there. The smallest positive eigenvalue is the Fiedler value. An associated eigenvector is one that's written right there below. Note, it doesn't matter what non-zero multiple I take because the same entries, whether they're negative or positive, if I took that entire vector that's listed there and multiplied by minus 10, right? Yeah, it's going to flip the signs, but the point is that the same entries relatively are going to have the same signs, right? So, for instance, what I mean is that looking at that vector, entries, the first entry, the third entry, and the sixth entry are positive. The second, fourth, fifth, and seventh entries are negative. And if I were to multiply that eigenvector by, say, minus 10, well, now my first, third, and sixth entries become negative and the others become positive. But the point is that they still have like sign, right? So looking at that vector, I have negative entries and I have positive entries. So what is the idea here? I say use the signs to come up with my desired partition. So in this example, entries 1, 3, and 6 of V are positive, and entries 2, 4, 5, and 7 of V are negative. This suggests the partition. This suggests the partition P, which is 136 in one and 2457 in the other. But hey, that's exactly the one that I had before. Right, 136 and 2457. So that Fiedler method comes up with a partition that does exactly what I was doing in my obvious method before, right? Removing the 2-3 edge. Okay. So that's a fully worked example showing exactly how this thing works. Okay. So this is the most basic version of the Fiedler method. You might have some questions here. So one obvious question, again, look at page 10 in chapter 13. So we end up with this Fiedler vector, this eigenvector that has a bunch of entries, and the entries are either positive or negative. Now the question is, what happens if they're neither? What happens if one of those entries is 0? Right? The question is, can that happen? Well, yeah, of course that could happen. This is just an eigenvector, and of course an eigenvector is allowed to have a 0 entry, right? It could have multiple 0 entries. So what if one of those entries were 0, right? So that we couldn't put it as either positive or negative when we're trying to associate what to do with a vertex. Well, in that case, we have to make a choice. Like, we would have to come up with a choice there. We would have to assign it either plus or minus as a sign. So we would have a choice there. That's one example of something that can go wrong. And so this little explainer paragraph on page 10 beneath the eigenvector says, at its most basic, the Fiedler method basically states that we can achieve a, quote, reasonable partition into two subgraphs by separating the vertices according to the sign of the values in a Fiedler vector V where each entry corresponds to a vertex. This means we group together the vertices I with V sub I equal positive, and we group together the vertices I with V sub I equal minus. And in the case that V sub I is equal to 0, we simply have to make a choice, okay, which is exactly what I just said. And again, it further says, by, quote, reasonable, we mean that an attempt is made to remove as few edges as possible while keeping the resulting subgraphs of approximately equal size. And it says it's worth noting the Fiedler method is not perfect, as we'll see, but often the problems that arise can be easily accounted for. Okay. And so there's a bunch more examples, but I think since it's almost 3:30, what I'll do here, rather than continuing on, is I will, since I've shown you kind of the basic Fiedler method, I will do a couple more of I'll read through a couple more of these examples. So you should read through them on your own, first of all, because the notes do a good job of listing out all these things, and I'm not gonna have you watch me copy a like 12 by 12 matrix. That'd be stupid. So I will read through these examples, but you should read through them on your own as well. But I'll do that at the beginning of a supplemental lecture that's going to branch into the cryptography bit with the chapter 14, which is the very last material. But you've seen how to do the basic Fiedler method here. Near the end of this chapter, so 13.4.6, so starting on page 16 and later, there's more involved examples that show you basically all the things that can go wrong. So it does an example of the bow tie that I did earlier. You should have a look at those if you want to. So you've seen enough to go through the problems that I've assigned if you read a little bit more on the examples, but I'm still going to go over more of these when I do the supplemental lecture. So I will do some of these examples for like maybe the first, I don't know, like 20-ish minutes of the supplemental lecture, and then I'll start and finish chapter 14 in one go, and that'll be that. So anyway, so that's the most of the graph theory stuff, but like I said, I'll finish with some examples when I post the lecture. So I'll be posting that in the next couple of days, and I'll let you know when I do it. So I plan on uploading your final exam on Friday, sometime on Friday, so that you'll have roughly like 5 days to do it. So, so yeah, just pay attention to announcements, and I'll post everything you need. So anyway, that's the first and biggest bit of the graph theory stuff. So I'll finish that stuff up later, and so I'll see you all. Well, I will post the recorded lecture, like I said, in the next couple days. So pay attention to announcements.